All right, in this video, I want to take you through the process that we go through in order to figure out which ions an atom is most likely to form. So we're creating here monatomic ions, and these are going to be ions formed from just one type of atom or just one element. So monatomic means one atom. And the two tools that we're going to use here is, number one, our electron configuration. We need to know what the valence electrons are. And then we're going to be using the octet rule for the main group, which is what most people do. Now, as we get into the the P and the D blocks, we're going to do some higher order thinking here. But for the first few examples, it's just the octet rule. The first element we have here is magnesium. We want to predict maybe what magnesium's ion or ions will be. This chart is a flow chart. It's more like an algorithm, a mental algorithm that I developed to help me think through what ions would form. So I hope it helps you as well. If we look at magnesium, given the electron configuration we have here, we count up the valence electrons. So we see 2, the 3 S ones. And then we look at the octet rule, that magic number of 8. If it's close enough to 8, you can gain whatever you're missing to get up to 8, or you can lose to get down to the inner core, which would be another 8. So in this case, magnesium would lose 2. And if that's the case, it would be a cation, Mg plus 2. Remember, you're losing negative charges. That's why that's a positive ion. All right, so that's the main thing. That's the most important thing to consider: valence, and then the octet rule. And then some other considerations that we have to go through is it a p metal? And I'm underlining metal here. And the answer is no, so we don't have to worry about that. Is it a transition metal? No. So for magnesium, we don't have any other ions that we have to worry about. In the next one, we have fluorine. So again, valence electrons. There's 2 plus 5, so there's 7. And if you have 7, it's going to be easiest if you gain 1. If you do that, it becomes F-1, or fluoride. Now, is it a p metal? It is a p element, but it's not a p metal. So let's worry about that. And it's also not in the D block. All right, so those are both main group elements, and they behave just according to the octet rule. So very, very straightforward. Now, as we get to the next few examples, we're going to have some transition metals. So here we have scandium. By the strictest definition, it has 2 valence. So to get rid of those, it will, as a metal, lose 2. So scandium could be plus 2. Now, is it a p metal? No, so we don't have to worry about the p block. But it is a transition metal. So there are 1 d electron. Now, when we deal with the d electrons, the magic number is not 8. The magic number is 0 or 10. You want to fill the whole thing up or empty it. If you can't do either of those, 5, which is half full, becomes an okay option. That's because there are 5 d electrons, or 5 d orbitals, I should say. And if we put 1 electron into each, that is half filled. And so that's sort of okay. There's no pairing up being done here. There's no empty orbitals, so that's plan B. So in this case, we're going to lose 1 to empty the D shell, which means scandium could also be Sc plus 3. Plus 3 because you still have to lose the valence first, or the outermost, and then you lose 1 more. So there's 2 possibilities here, plus 2 or plus 3. It turns out that scandium in nature is almost always the plus 3. And we don't really have any way of knowing that just by our predictions here. So I'm just kind of giving you some heads up when we come into situations like that. All right, manganese. Valence, again 2. So it will lose 2 and be Mn plus 2 cation. It is not a P, but it is a D block metal. So we have 5 Ds. it's going to stay. He wants to have 5, so it's not going to do much else. So manganese typically is just the +2 when it's in its ionic form, and of course it can have multiple oxidation states when it does more covalent bonding. Zinc, 2 valence, so it is going to lose 2 just like the rest and form Zn+2. It is not a p metal. It is a D, and there are 10, so it wants to stay at 10, which means zinc will also only do +2. That really is all zinc ever does is +2. Okay, selenium is next. We count up here. We have 6 valence. That's the 4s2 and the 4p4. So we're going to gain 2 as a nonmetal. So selenium will be Se-2. Now it's not a p metal. Selenium is a nonmetal, and it's not transition. So that's all it will do, and that becomes the selenide ion. Let's make sure that looks like an E. All right, iron. We count them up. Iron has 2 valence by the strictest definition, so we'll lose 2. And iron could be +2. It is not P. It has 6d electrons, so it would want to get to 5, which means it would have to lose 1. So possibly iron could be +3. And it turns out in nature that iron indeed does both of these ions. +2 is a little bit more common than +3, but it's not like +3 is rare or anything. The next one is gallium. So gallium, if you add up the valences, we've got 2 here and 1 here, so 3. 3 is still closer to 0, so we will lose those 3. And then gallium will be a +3 ion. Is it a p metal? Well, yes, it is. It is a p metal. So we could go through this. I'm going to say yes here to show you how this works. Okay. How many would it gain or lose to make p happy? Well, like we did with the D's, where the magic number was 0, 10, or 5, which is full, empty, or half full. The P's hold 6 electrons. So for them, the magic number for p would be 0, 3, 6. That's full, empty, and half full. So for gallium, it would lose 1. Okay, it's not a transition. So gallium theoretically could be +1. It turns out in nature that can happen, but very rarely. The +1 ion is actually kind of rare, but we predict it as a possibility. All right, then we have cesium, 1 valence, lose 1. Cesium is just +1, not a P, not a transition. That's all cesium does. And then finally, for lead, if you carefully pick out your valence, it's going to be here and here. So we have 4. Now 4 is an interesting number. 4 is exactly halfway between 0 and 8, so you would think that lead could go either way. And that's sort of true for elements in this column. However, lead is a metal, which means it has a low electron affinity, so it's not going to gain. It's actually going to lose. Metals only lose. So we could say that lead could lose 4. And maybe would be Pb +4. Is it a p metal? Absolutely. So we're going to put yes. And it wants to empty the p in this case. It's got 2 p's. 0 is what it wants to do since it can't gain. So it would lose 2 here. And if it did that, then lead could also be a +2. It is not transition. Which one is more preferred? Well, it turns out that lead is almost always +2 in nature, because the +4 is just hard to do. There's also some interactions with the F block electrons there, the 4F14, that contribute to the +2 ion being more favorable than the +4. It's not impossible, but it's very unlikely in nature to find the +4. You can find the lead +4 in the oxidation state, but again, usually not in the ion form. The moral of that story is, for the P metals, as you get closer to the bottom, it becomes less about emptying the valence shell and more about just emptying the P subshell. Okay, I'd like to show you one more little thing here. That's some little trick a lot of transition metals do. In this case, if we look at copper, it's got 2 valence, and so lose 2, and we would say copper would be +2. And frequently in nature, that's exactly what copper is. It's not a P, so don't have to worry about that. It is a transition. So here we have 9 Ds, and your gut instinct is to say, well, it's going to gain 1. Well, it's a metal though, so metals never gain. You can't gain. But copper has come up with a little trick, and what it can do is promote 1 to get 10. And what it's doing is really reshuffling its electron configuration. It goes, instead of 4s2, it says, well, let's put one of those s electrons into the D. That's why it's called promotion. And now you only have 1 valence, and so you can just lose 1. And we see that in nature, copper does indeed do that. For copper, the +2 ion is actually still the most common, but copper's family member silver, right below it on the periodic table, has the same arrangement of electrons, but it turns out that silver only does this promotion. So silver would only ever be +1. And there's not a real good explanation as to why that is. What is it about silver that only promotes, whereas copper can do either one? Those are the little things about chemistry you have to learn with experience, but I hope this helps you figure out monatomic ions.